Good evening, class. Section 4.2, we're going to talk about two more theorems. One theorem is Rolle's theorem, and the other theorem is the mean value theorem. Rolle's theorem says we need to let f be a continuous function on a closed interval, and it has to be differentiable on the open interval. Okay, the closed interval goes from A to B, and the open interval goes from A to B as well. Please remember the difference between a closed interval and an open interval. A closed interval, remember, it includes the endpoints, and an open interval does not include the endpoints. So if f is continuous on a closed interval from A to B and differentiable on the open interval from A to B, and if f of A is equal to f of B, then Rolle's theorem says that there is at least one number C in the interval from A to B, the open interval from A to B, such that the derivative evaluated at C is equal to 0. Okay, f prime of C is equal to 0. Okay? So when we're looking at theorems in mathematics, you're always going to have conditions. If we're going to use Rolle's theorem, we have to first know that 1, f is continuous. Not only continuous, it has to be continuous on a closed interval, some closed interval from A to B. Second condition is that the function has to be differentiable on the open interval. Notice that it's an open interval, and so it does not include the endpoints. So it does not have to be differentiable at A or B, but it has to be differentiable at every point in between A and B. Then there's a third condition. The third condition says that f of A has to be equal to f of B. When these three things happen, then there's guaranteed to be a number C such that f prime of C is equal to 0. And that number C is going to be in the open interval. Now remember, when we discussed section 4.1, when f prime of C is equal to 0, that means that C has to be a critical point or a critical number. Okay? So what this is saying is we're guaranteed to have at least one critical number when these three conditions are met. Okay? So let's look at this graph to the right. I drew it's kind of a curvy graph, but if you can notice, my graph of f is continuous between A and B. There are no breaks in the graph. And if you also notice, f of A is equal to f of B. This is my f of A, and it's also my f of B. You also notice that there's a point right here. There's a hump here, and I know that this is going to have a horizontal tangent line, and there's a point there. There's a horizontal tangent line as well. Horizontal tangent line means that the slope is equal to 0. The slope of the tangent line is equal to 0, which means that f prime of, I'll call it C1 and C2, has to be equal to 0. So in my graph, I have two values where the slope of the tangent line is equal to 0 or the derivative of the function is equal to 0. Okay? And also you will notice this point right here is a relative maximum, and this point right here is a relative minimum. So Rolle's theorem helps us to know that there is a relative maximum or a possible relative maximum or relative minimum within a closed interval. Okay? But remember, these three conditions have to be met. Here's an example where we will be using Rolle's theorem. Determine whether Rolle's theorem applies. If Rolle's theorem applies, find all values of C in AB such that f prime of C is equal to 0. Okay. Here we have a problem. It's a function that's the graph is going to be a parabola. It's a quadratic function. And the closed interval that we're looking at goes from 2 to 6. Okay? So we're looking at this quadratic function as it goes from 2 to 6. Now, remember, before we can use Rolle's theorem, we have to determine whether or not the three conditions are met. The first condition says that 1, we need to make sure that f is continuous. Is f continuous? More specifically, is it continuous on the interval from 2 to 6? And the answer is yes. Okay, we have a parabola. We have a quadratic function. It's a polynomial function, and the polynomial function is continuous for all real numbers. So, of course, it has to be continuous from 2 to 6. The second condition was that the function had to be differentiable on the open interval from 2 to 6. So the question is f differentiable on the open interval from 2 to 6? So remember, when you're wondering if the function is differentiable for Rolle's theorem, we're only considering all of the points in between 2 and 6. It does not have to be differentiable at the endpoints. Well, to determine whether the function is differentiable, let's go on and find the derivative. The derivative of the function is going to be f prime of x is equal to 2x minus 8. And if you look at that derivative, you see that if I plug in any number between 2 and 6, we get a value regardless of what number we plug in there. So yes, we can say that the function is differentiable on the open interval from 2 to 6. So we're going to put a check mark there as well. Number 3, third condition says that f of a, in this case a is going to be 2, so we want to check to see is f of a or f of 2 equal to f of 6. Well, how do we check that? Well, all we do is we plug in 2 and 6 into the function and make sure that they're equal. So let's see what f of 2 is. F of 2 is equal to 2 squared minus 8 times 2 plus 5. We end up with 4 minus 16 plus 5. 4 minus 16 is a negative 12 plus 5, and we end up with a negative 7. Well, let's see what f of 6 is equal to. F of 6 is equal to 6 squared minus 8 times 6 plus 5. 6 squared is 36 minus, this is going to be 48, plus 5. 36 minus 48 is negative 12 plus 5. And I end up with a negative 7. So you see that f of 2 is equal to f of 6. And so we can check that off. So we see that all three conditions are met. We see that f of 2 is equal to f of 6. We see the function is continuous. We see that the function is differentiable on on the open interval from 2 to 6. Okay? So we know that Rolle's theorem applies. Now that we know that Rolle's theorem applies, we know that there has to be at least one value C within the open interval from 2 to 6 such that f prime of C is equal to 0. So our next task is to find all of the values of C. I'm going to rewrite the derivative in terms of C. So this is going to be f prime of C is equal to 2C minus 8. And we want to solve that where it's equal to 0. So 2C minus 8 equals 0. Add 8 to both sides, we get 2C is equal to 8. Divide both sides by 2, C is equal to 4. We're going to have to make sure that our C, or the value that we find, falls within the interval from 2 to 6. C does fall between 2 and 6. So this is the C value that we found. All right, here's another example for Rolle's theorem. Again, we're going to determine whether Rolle's theorem applies, and if it applies, then we're going to find all the values of C such that f prime of C is equal to 0. This time we have a trigonometric function, f of x equals the secant of x, and we're looking at this function over the interval from pi to 2 pi. Okay? So we're going back to our three conditions. The first condition that we need to make sure happens is that f is continuous on the interval from pi to 2 pi, the closed interval from pi to 2 pi. Well, let's look at this. Now, we really don't even have to look at the graph per se, but f of x equals secant of x. Well, we know that secant and cosine are reciprocals, so that's 1 over the cosine of x. Okay? Well, this function you see is undefined wherever cosine is equal to 0. And if you recall from your trigonometry that cosine is equal to 0 wherever, if you look at the unit circle, that's supposed to be a circle, but whenever your graph hits the y-axis on the unit circle, that's going to be pi over 2 and 3 pi over 2. Okay. Also, you know, it's going to be actually odd pi over 2s, odd values of pi over 2. So it would be pi over 2, 3 pi over 2, then 5 pi over 2, and 7 pi over 2, and negative pi over 2, negative 3 pi over 2. Those are all of the values where cosine is going to be equal to 0. Well, notice that 3 pi over 2 falls between pi and 2 pi. So our first condition is not met. I know that f of x is undefined at x equals 3 pi over 2. Well, if the function is undefined there, then that means that the function cannot be continuous there. And so Rolle's theorem does not apply. So we can stop here. There's no value of C. There's no guaranteed value of C in that interval from pi to 2 pi, so that we can find a value where the derivative evaluated at C is equal to 0.